Alright, hi y'all. Today we're going to be going over this EM2 practice problem from exam 1. And this is from 2024, spring 2024, and this is a current exam practice problem. So, I guess we can get started here. We have an electron beam of radius A flowing along the z-axis, and as we can see here in the figure, the volume charge density inside the beam is given by whatever that is here, and it says the velocity of the electrons is in the z direction, and the magnitude of it is v naught. Okay, so with all that information, they want us to solve for the current density vector j. So from class, these two equations should come rather naturally. We have this equation where the current density vector is equal to the current divided by the change in cross-sectional area. Of course, we have current density vector, right? This would make sense if if we had a surface, or not a surface, if we had a current. And we don't have a current, so we can't use that. There's another equation here, rho v times v, the v vector. And of course, this is going to be our charge velocity equation, which we'll use because we're given the charge density and we're given the velocity. So what is rho v? Well, rho v is given by that equation. Okay, and we're dotting it with velocity vector, which is v0, that's the magnitude, and our direction, z direction. Okay, so right away, this is a very easy question. This should give us free points. A v0 over 1 plus rho over a squared. And we have to remember what are our constraints. It says rho less than a, less than or equal to a. And what are the units? Well, let's think about this here. Looking for the current density equation, or I guess equation, right? Our answer here. What did we do here? We have our charge density, which is given to us as coulombs per meter cubed, and we're multiplying with the velocity, which is, of course, meters per second. So this meter cancels out with that meter. What we have left is coulomb per meter squared times seconds. Well, what else do we know? I mean, you could leave it like this, but there's a better answer. You could now change coulombs per second, the rate of charge, equal to amps. That's what an amp is. That's the definition of an amp. Okay, amps per meter squared. And that's going to be our answer here. Okay, now for part B, what are they asking us? They're asking us to find the total current, IT, in amps, of course, in the z direction. Okay, what are the equations that we know for I, for the current, total current? Well, the one equation that stands out is I is equal to the integral, the surface integral, of the current density vector dotted with the normal vector that we see with respect to S, the surface area. Okay, so do we now have the current density vector? Yes, we do. We solved for it in part A. Do we know what direction is? The normal direction, or this unit vector here. Well, yeah, they tell us it's in the z direction. Perfect. So we take the dot product between the current density vector. Oh, shoot, you cannot forget this. I almost got points. My bad. You cannot forget the direction of our current density vector because it's a vector. Can't forget that. Get probably a bunch of points off for that. My bad. But when we take the dot product between our current density vector, which is going solely in the z direction, and dot it with the unit vector z, what we get is just the magnitude of the current density vector. So what we get here is the double integral, because we're taking a surface integral, of just the magnitude of our current density vector. Of course, with respect to S. But what is S? Well, we're in cylindrical coordinates. We're in the 2D cylindrical coordinates, which is rho d phi. Now, rho is going to be your sort of radius. So what we have is from 0 to a, because you have a cylinder with surface area of a circle surface area, which is the radius of a. Now, the angle at which you go around, which I can draw here, we have our radius A, but when we take the angle and we go around the circle, this is from 0 to 2 pi. So that's going to be our second bounds of integration. Now we have to take the integral of our current density vector times rho with respect to rho. So let me write this out in, I'm going to kind of write this out by itself. Everything is on the outside, or AV0, that doesn't have to deal with rho. So it's rho over 1 plus rho over a squared, right? Because we have this rho being multiplied. AV0, AV0 has nothing to do with rho, so we can take it out. And now we want to take this with respect to rho. First thing that stands out in my mind is do u sub. But what do we do with u sub? Well, we can set u equal to rho squared over a squared. You could also let u equal rho. You would then have, u over 1 plus u over a squared. But does that really help you? Not really. You're just in the same predicament you were before. So why not distribute that squared value? And now you can say u is equal to rho squared over a squared. I guess you could also just say u is equal to rho squared if you wanted to. I'm going to leave it like this. But what we get here is that du is equal to 2 rho over a squared d rho. Thus, d rho is equal to du a squared over 2 rho. So now what we have here is AV0, the integral from 0 to a of rho over 1 plus u times, we will replace d rho with du a squared over 2 rho. All right, and so what do we notice here? Well, the rho's cancel. That's exactly what we want to do with u sub. The a squared has nothing to do with rho, so we can move it to the front, outside of the integral. And what we get is a squared a v naught integral from 0 to a of 1, or I guess the 2 can come out also, right? 1 over 1 plus u du. Well, this seems easy enough. That's just natural log of 1 plus u. So we have a squared av0 over 2 times, or I guess I could bracket here, natural log of 1 plus u from 0 to a. Now, we have to make sure and plug u back in. What was u initially? Rho squared over a squared. So what we get is a squared a v0 over 2 natural log of 1 plus 2 rho over a squared. Or no, u is rho squared over a squared, sorry. Rho squared over a squared from 0 to a. And now you plug in a for rho. So now you get a squared a v0 over 2 natural log of 1 plus a squared over a squared minus natural log of 1 plus 0 squared over a squared. Okay, so now this becomes what? 0. Natural log of 1 is 0. So this entire thing can become 0. And now what we have is a squared a v0 divided by 2. A squared over a squared is 1. Natural log of 2. And that's what our integration comes out to. But remember, this is a double integral, so we have to come back and take this another step further. Integral from 0 to 2 pi of our resulting integral here, a squared av0 natural log of 2 divided by 2 with respect to phi now. Well, we don't have any phis, so, we can just say the integral of 1 is phi itself, so 2 pi minus 0 is just 2 pi. So now we're left with 2 pi a squared a v0 natural log of 2 divided by 2. And of course, the 2's can cancel, so we're left with pi a squared a v0 natural log of 2. And what are the units for current? This will be amps. So that will be the total current that, what does the question exactly say? This is the total current flowing in the z direction inside of the beam. Okay, hopefully this made sense. This was, I definitely went a little bit further into the double integral in this part. If you're able to do this double integral quickly, it should be that's all this question was. All right, part C now. Part C, it says, find the current in amps that flows upward through a small circular surface S of radius sigma. I believe that's sigma, right? Where sigma is much smaller than A. So we have something where sigma is much smaller than A, and it's centered on the z-axis. Their surface S is tilted at an angle at 45 degrees up from horizontal. Okay, so this is going to be something similar to what we saw in class. We have our current density vector, or our current, is going up, and we have an angle that is like this, that has a surface, right? Where the angle here, theta, is 45 degrees. So what is that going to be? Well, that's going to be what? Cosine of 45 degrees. So we're going to take the regular schmegular current through that surface and multiply it by cosine of 45 degrees because that's the effective current. We could solve for the total current, and that would, entail cosine of 0, but it's not going through that surface at a 0 degree angle. It's going at a 45 degree angle, and this is going to be square root of 2 over 2 or 1 over square root of 2. So we're going to multiply at the very end our answer to 1 over square root of 2. Now, what does it mean when it's saying that the radius of this surface is much less than a? Well, what this means is when we take our integral, remember how we had this original current density vector, which is rho over, or sorry, not rho, a 1 over 1 plus rho over a squared? I'm going to do the same thing here where the current, this is the surface current, sorry. I guess it is a surface current, whatever, is going to be equal to the integral, the surface integral again, of the current charge density, not the current charge density, the current density vector, dotted with, the norm, the vector is going, the angle it's going at. And of course, we know the dot product is the unit vector times the cosine of the angle between them. We know the angle between them is cosine of 45. At the end, we'll multiply that. When it says the this radius is much smaller than a, what it means is, I'll write this out, the integral here, or I guess the double integral, right? We have 0 to 2 pi again, but this is from 0 to a. What this means is that the a value is going to be, or not the a value, the rho value that we have at the beginning is not going to be rho. It's going to be the sigma, which is much smaller than a, right? So what we can do is we can rewrite our equation, or maybe not rewrite it, but say it. So what I'm trying to say here is that the current that we're going to get is, of course, going to be equal to the surface integral of the current density vector dotted with the direction it's going, ds. But this area is so small. We see in the problem it says that where the sigma value is much smaller than a, because it's so small, we don't have to worry about the integral. What we can do is we can say the current density vector, where we can plug in sigma instead of, do the integral, we can dot it with the direction it's going and take the area. ds will become delta s. Do you remember earlier where we talked about j, or not j, I guess it is j, yeah. J is equal to I over delta S. We're going to be using this equation because it's such a small area. Hopefully this makes sense. because what we're going to do here is I is equal to now j times delta s. So that's what we're going to be doing here. We don't have to take an integral of a large area and find the summation of the currents. What we can do is, because the area is so much smaller than a, is we can then take it to be just this. Okay, so hopefully that made sense to y'all. What we can then do is do what? Pi sigma squared, because this is the area, the cross-sectional area, with radius sigma. But what is j sigma? Well, let's see what j is. Well, the current density vector is just like we've done before, a v0 z hat divided by, what is it, 1 plus, well, not rho anymore, it's going to be sigma over a squared. Okay, and we dot it with the z vector because that's the direction it's going in, pi sigma squared. What can we do here? The first thing that comes out to mind is we can simplify this. We can say this here is sigma squared over a squared, multiply top and bottom by a squared, and of course this becomes a 1, right? We can then say a v0 a squared over a squared plus sigma squared. And what do we know? What do we know that what we're given? We're given that sigma squared is so much smaller than a, or not sigma squared, but sigma is so much smaller than a. So because sigma is so much smaller than a squared plus sigma squared is essentially just a squared. So what we can do is we can rewrite this equation as a v0 a squared over a squared. And now this becomes 1, and this becomes a v0 left over. So then we can plug this back into the equation, replace it here, and we're left with the current being equal to a v0 and oh shoot, I forget the natural log of 2. Oh wait, no I didn't. No, that's the current from the last one, sorry. A v0 here, and we have pi sigma squared, or oh, that's a delta. What am I talking about? Lowercase delta. My bad, my bad. And we have, of course, we have to multiply by cosine of 45 degrees. So now our I current through that surface S is a v0 pi delta squared divided by the square root of 2. The current unit is amps. So hopefully this last part was definitely kind of fishy, mostly because the area, or the value, the radius of the surface is so small that there's a lot of things you can neglect. And it definitely doesn't feel right, but this is the way he did it, so I'm just going with what he did. I'll probably ask him about it in class to make sure I kind of understand, when you can and can't do this, or maybe just look back at the notes. But yeah, the big takeaways from this are you have to know how to find the current density vector using the equations, both of these equations here. You also need to know how to find the total current using integration. And finally, we have to remember when the current density vector is not going in the same, or is not perpendicular to that surface, we have to remember to take the cosine of that angle, because that is our effective current, or the effective current going through that surface. So those are the big takeaways in this example here. Hopefully y'all understand. If y'all have any questions, please leave them in the comments. I'll probably do a couple more of these practice problems before the exam happens. There's probably not going to be for a while anyways, but better to get started earlier than be late, having to cram. So, thank y'all for joining.